Let me emphasize that the projector software is not written in Julia. It would have segfaulted a while back, I think, if that was the case. So yeah, I'm talking about Flux, which is a machine learning framework I've been working on, which mainly at the moment focuses on the kind of the interface and the way you use the framework. So I'll give you a quick taste of what it looks like and then kind of try and motivate that a bit more. So the point with Flux is that we can basically write normal-ish Julia code and run it on, say, TensorFlow or MXNet or another kind of graph-based framework as a backend. So we have a normal Julia function like x.times x, which does an element-wise multiplication. We can call that function. And if we call it, it's just Julia code, so it runs within Julia. But we can also convert it and say, run this thing on TensorFlow. And we get the same results, but converted to floats, because that's what TensorFlow works with. And then we can also do things with that, like making a gradient and finding out what the gradient of our function is. In this case, 2x, because it's an element-wise squaring operation. So what I need to explain is why this is different from how you normally use TensorFlow and why that's interesting. So the way you normally use TensorFlow is you build a graph. So in this case, we have x is a placeholder, y is a placeholder. We multiply those two kind of lazy values together, and we get z. Z kind of represents this lazy value, and then we evaluate z, and we, with the placeholder, set to some inputs, and we get a result. This is obviously very different from how we normally do programming. There are good reasons for doing it this way. We need kind of a data flow graph in order to understand more about our computation, what it's doing. So that's why people write frameworks in this way. But it has some downsides. So the idea, in this case, it kind of looks like these two things are fairly similar, right? You're just writing Python code and you run it with these placeholder arrays. But the thing is that this is kind of quite a leaky abstraction. So fundamentally, code that's written in this way has two runtimes. The first runtime, you build up the graph, and the second time, you execute the graph with real values. Now, in some sense, most code that you write has this kind of thing going on under the hood. So if we write Julia code, for example, when we run that, there's a first runtime where we work out the types and kind of interpret it with type information in order to optimize things. And then you run it with values in the machine code. So it's effectively similar. But the thing is that when you work in Julia, you don't have to ever think about that that type stage, right? You don't have to reason when you're looking at code about the fact that types are running through it too much anyway. So in TensorFlow, you very much, with the API it has, you very much do have to reason about that. And so when you're looking at code, you have to figure out the fact that it's running once with graph and then it's running twice the value. When you see TensorFlow tutorials, they always explain the graph building step because it's fundamental to how you think about this code. And that can get pretty hairy to work with. You have to think about this distinction and juggle it in your mind when actually code with one runtime is usually hard enough to understand. So we can't use our standard workflow and tools. We can't use the Python debugger to run through TensorFlow code and see what the values are doing because that's not happening in Python. It's also TensorFlow or MXNet doesn't have Julia stack traces, so you can't pinpoint where errors are coming from and things like that. You have different APIs for things like doing a sum. Are you doing a sum on a TensorFlow value or on a Python value? You have to choose between those different things. Also control flow. So you read code and it might have a Python while loop and a TensorFlow while loop. These are happening in different runtimes. You have to juggle that. And more importantly, it's kind of hard to build abstractions on. So this is a more subtle point, but I think it's kind of empirically, there's empirical evidence for this in the fact that people write so many TensorFlow wrappers, which kind of, rather than working with the rest of the TensorFlow abstractions, kind of completely hide them. And so I'll show you how Flux avoids that. So here's a simple example, right? Here's a very simple model, linear regression in Julia. And the exact mathematical form of this isn't that important. But the point is we have some simple mathematical Julia code which expresses this idea. And so you can kind of write TensorFlow in a way that looks like this in the simple cases, and the tutorials will show you this. But it gets a bit more complicated if we want to do things like dealing with these multiple runtimes, if we want to kind of do things like scoping variables so that we can reuse parts of the network. So TensorFlow has no idea about Python scope, so you have to do that explicitly. And in order to debug, you name all of the operations in your graph so that you can then go back and pinpoint where that error happened. So if we apply all of these practices that do come up in real TensorFlow code to a simple model like this, the code that comes out is more like this. And you can see pretty much straight off the bat that the problem we're solving when we write this code is not dealing with the machine learning model. The problem we're solving is dealing with TensorFlow and trying to get that to behave properly. And then the difference in Flux is that we can go back to this kind of, the more kind of naive code that we wrote before and basically rewrite that, but with the @net annotation that gives you the data flow interpretation of that function. And so the code is shorter, it's nicer, it's easier to reason about. You don't have the distinction between the two runtimes because we can do things like overloading while loops and if statements to do the right thing, regardless of where you're running and how and what kind of values you have. And of course, this means you get stack traces, right? So when you get an error in the TensorFlow graph, in TensorFlow or MXNet, this tends to be all you get, this error message or a couple of stack traces that tell you different things or something like that. So if you get an error in Juno, then it will figure out where the error actually came from in your Julia code and give you the error message pinpointing that in your Julia code, right? No Julia code is running here in this example, but we can still get the error message. So that's kind of the basic idea and gist of it and the motivation. I'll kind of show you a slightly more complex example where we do some more interesting things with this. So going on to RNNs. So I spoke about this a bit yesterday, but RNNs are what we use when we're processing sequences, like sequence data. So voice, like frames of voice, frames of audio in a sound file, or characters of text or words of text in a sentence if we're doing a translation system. That's how these kind of things work. So a recurrent net, it's essentially a very simple concept. Instead of having a pure function which always gives the same result for a given input, we have a function which carries around a kind of state. So in this case, we have a flux net function which says, well, so we have this time indexing construct. And so we want the value of count, but we don't want the value of count from the current time the function is being called because that's circular, but we want it from the previous time the function was called. And this, intuitively, you can think of this as being a lot like a global variable, but it's kind of encapsulated to that particular function. And so if we try and call that, we'll get an increment. We'll find that the count variable increments every time we call the function. So the crucial idea here is that if our function is recurrent, it can store some state, not just about the current input, but about all of the inputs it's seen in the past. In this case, that's a trivial count of how many things we've seen, but in a machine translation model, for example, we'd feed the model a word at a time, and it would store some state that says, here's where I am in the sentence, here's what that sentence means. You can use this, so this is kind of a more complex example where we use the syntax. So on the left here, there's a very blurry, unfortunately, a screenshot of the equation that's coming from a paper describing the LSTM, which is a more complex kind of recurrent network. And on the right is the LSTM implemented in Flux. And you don't have to really understand this code in depth, but the core thing to take away is that this is really, really close to the mathematical description. And if you find an LSTM in basically any other framework, you'll find that it's at least 100 lines long. So what I want to do, this doesn't implement every optimization possible and things like that, but I want to take it in that direction and make it so that you really can write this kind of code and get a good machine learning model out of it, where you would have had to write hundreds of lines before. So this model, just to show you what these things can do, you can actually give these models, and I talked about this a bit yesterday, but you can give these models a character at a time of text and ask them to predict the next character in the sequence, and they will eventually learn to model the kind of text that you're feeding into them. So for example, you can train this on Julia code, and then you can feed the output of the network back into itself so that you're just predicting things at random, and you end up with kind of strange, dreamlike text that's generated by the network. So I actually trained this on Julia code. And what's amazing is that this very simple model can actually, despite just this is just one character at a time, right? We give it an F, it says U. We give it a C, it gives T, and so on, right? But it stores enough state to know where it is in the sequence, where it is in the code. So it learns things like indentation. It learns things like if you're inside a function argument call, then it should have a type parameter. possibly 2 in this case for some reason. My favorite thing by far is the names it comes up with, because they're brilliant. Like the function unpuff, I don't know what that does, but I want to know. Yeah, if someone wants to implement like cannot T1 and like tell me what that does. Yeah, read it out. Yeah, it's all good. It's all good. So yeah, this model's up online somewhere, so like you can play around with it and like see what it generates. It's pretty fun. I'll show you a slightly more complex example, which is an encoder-decoder. So this is a more complex kind of model where we essentially have a recurrent network to which we feed like the characters or words from a sentence. We feed one at a time, and at the end of that, we take the state that the network built up. Then we give that encoding of the sentence to another network, and we run that a few times. It gives a different output each time, and that output will be the words of another sentence in another language. And so we can use this for things like machine translation. And this is kind of like the state-of-the-art system that's used by Google, for example, in their Google Translate. So I actually applied this kind of system to phoneme translate. Oh, yeah. So this is the implementation in Flux, basically. And so the core thing to take away from this is that so in most other frameworks, you have like an API for a lot of different things. So for example, in TensorFlow, there's like a seek-to-seek API and a sentiment API and so on. So the important thing about this is that within this code, we've basically written fairly normal-looking Julia code. So for example, we have an attention mechanism. So for each token in the sentence, we take the token and do an alignment. Basically just calling a function with each token from the input sentence. Note also that we've got the state t-1 inside that closure that we used for the map. So dataflow.jl, which is underneath this, supports closures inside Dataflow graphs in a fully generic way. So you can kind of inline those closures and then work with TensorFlow or something else and do like these kind of crazy things. So that's quite nice. And yeah, this is again like a very simple, straightforward implementation that doesn't come from like a custom API, but just comes from 2 very simple concepts, which is having a recurrent network and having some unrolling of that network. So we don't need custom APIs for everything we do. I applied this particular model not to translation, but to a kind of phoneme translation. So there's a data set called CMUdict, which gives you a dictionary with about 130,000 words and an encoding for their pronunciation. So each of these things represents a phoneme. So for example, AA gives you R, and it gives you specifically R, whereas just the letter A on its own could be A or A or something else, right? So we narrow down exactly how we pronounce the sentence in American English. So I'll show you a couple examples of this. So we can go through and, for example, obvious things. It predicts arm as arm. It also learns, so part of the CMUdict is emphasis. So if you have a 1, then that means stress that syllable. If you have a 0, it means unstress it. So we predict hello, we predict John. I apologize, by the way, for the American pronunciation. John. It gets a verse slightly wrong. This is a bit trickier. This is not an unreasonable pronunciation of the word averse, right? So it's saying a verse, which I think maybe some people even say it that way. So that's not a crazy thing to think, even though it's wrong. Yeah, phoneme, and like we can make up words like chami, and like it comes up with a reasonable pronunciation for that word, even though it doesn't exist in CMUdict. It's not a real word. It learns, for example, so this is quite complex, right? Because these 2 words, we think about them very differently and pronounce them very differently, even though the difference is actually only 1 letter. But we pronounce one as thrice and one as thrick, which is also not a real word. But the model is kind of learning that you can take that one change at the end and like push it back through the sentence and come up with a different pronunciation for the whole thing. If anyone has any like suggestions for what to put into this thing, by the way, I can try that out. Any takers? Wine? Let me try that. Oh, no, wide? Oh, wind. Okay, sorry. I can't hear well from up here. Wind. Ah. Trick question. No, because I've trained this on individual words, so I couldn't. You could do one word at a time, but you couldn't do it on multiple words at once. Winding, yeah. Winding. That's kind of valid. I'll try Ranjan's name. What's this? Anantamals. So about the same level of pronunciation of like a US English speaker there for Ranjan's name. Let's try. So this is interesting, right? Because the model is just as confused as we are. Okay, let's. Sorry? I think that might be too long. And I can't type it.
It'll be a buffer overflow.
Let's try that. I'll let you decode that one. Okay. So going beyond. So I think having Flux and having like these higher level ways of doing machine learning is really, really important for our ecosystem, and it's a crucial part of that. But it's also certainly not the only part. There's a ton of stuff that needs to happen in order to kind of make this really good. And so I kind of want to talk about the other things that I would like to see happening and would like to kind of push along, and where we see like the machine learning ecosystem in Julia going. So to introduce that, I want to talk about like a trade-off that you make when you choose deep learning libraries right now. So on the one hand, you have Dataflow based, which is the kind of thing I've just been showing you, things like TensorFlow, where you kind of build this graph and then execute it. And on the other hand, you have Autograd based, like PyTorch or KNet, one of the excellent frameworks we have in Julia for this, in which you write normal code. You write like it's like normal Python code or normal Julia code, and you basically have a live differentiation of that code. And for technical reasons, these two things have quite different trade-offs. So on the one hand, you can get loads and loads of optimizations out of the Dataflow approach, but on the other hand, it's quite hard to, you're inherently limited when you do that. It's because you're going within that Dataflow model, and it's like, what can you express within that Dataflow model? Well, not everything, not necessarily every for loop or every control flow construct you might want to build. So you kind of have this split between, like, say, a lot of institutions right now, they have the researchers doing like PyTorch or something like that, and then on the other hand, you have like the deployment people doing TensorFlow or something similar to that. So yeah, if only there was some way of combining those two things. So in this what I've creatively dubbed the two framework problem, I think that we're kind of by having this Dataflow approach, we're actually getting a lot closer to unifying these two things, because in like the Flux approach to machine learning, you just have a function that you call and get an output, which is the same thing as you do in the Autograd-based approach, right? They're just implemented very differently, but they can have the same API and the same interface. So you can start building tools which are able to make use, like you can build optimizers which are shared between different approaches, which is kind of not really happened in the Python world, where each framework is its own island, its own kind of separate thing with its own GPU arrays and its own optimizers and so on. So I think, and kind of going further than that even, I'd like to get to the point where something like your average deep learning framework is really just actually a parametric type. So, and this is doable, right? We can have a tracked array which does Autograd, and a pooled array which does some kind of custom memory management, and a GPU array which gives you arrays on GPUs. And if we do this, we'll get all these features just splunked together, and we can use that, right? And so this is exactly the kind of thing you can't do in a language like Python, because if you try to do this in Python, have separate libraries for each for doing one thing, you end up sandwiching the Python interpreter between them. So you can't make modular libraries, you can only build these monoliths. But in Julia, you can kind of just like take these Lego blocks, combine them together, and Julia will compile custom code for that combination of things, right? Effectively, you're generating a deep learning framework on the fly. And that's it's both kind of obvious if you program Julia that that's what happens, but it's also a bit like mind-bending that that's possible. The other thing that I think is really interesting is the ability to compile, like JCompile Julia code to GPUs. So this has had, like obviously all of you will know that in the CPU world, this has had a huge impact because we no longer have to vectorize and things like that. It's kind of amazing actually how like relatively naive most deep learning frameworks are in terms of optimization. Most of them don't do much more than the NumPy model of saying, batch all your stuff together, have a really big array, and then your interpreter overhead is kind of amortized. But that's not enough for solving all problems. So if you can JIT your GPU kernels, you can do things like JITting a custom kernel for a fused operation, like broadcast fusion as we have now. You can do things like compiling whole networks to GPUs. You can do things like using multiple instruction, multiple data, as well as SIMD on your GPU, right? Where currently you can only pipeline instructions. So we're kind of only just beginning to explore what's possible with that, but I think that's going to be really exciting and interesting in the future. So finally, like this is like the summary of all this, and like what I think the dream is for us to build in Julia and what we should be aiming for in our machine learning ecosystem, which is to build a kind of frameworkless machine learning environment. We shouldn't have like big monolithic libraries that do all of this stuff. We should just be able to write Julia code, and we should be able to combine Julia packages and like have stuff work, right? And this is powerful because you can then take stuff and reuse it. You can use reverse diff and do deep learning with it, but then you can also use it for Celeste and map the sky, right? And you have these more reusable pieces. And so with this approach, we can attack more problems. We can attack more level of abstraction. Rather than being fixed at one level, we can go lower and do GPU kernels. We can go high level and do unrolling and all kinds of like really elegant models and things like that. And everything is kind of like, nothing is a black box here. You can kind of hack on all of this and see what's going on. So that's kind of where I want this to head. There's a lot of work to do to kind of get to that point, and it's going to take some time, and we're not there yet. But that's where I'd like to see us going. So thank you very much, and any questions?